Okay, we're gonna continue on. Six. Look at those six. Why not? All right. So last time, before the exam, there we talked about chapter 6, and we got into obviously nomenclature in that chapter, and we were talking about bonding. I think is where we sort of left off. So remember, we talked about two types of bonding. We have ionic bonding, and ionic bonding is always between a metal and a non-metal. And because of a lot of those sort of periodic trends that we talked about, I think in the previous chapters of that, metals pretty much have all the periodic trends like ionization energy, electronegativity, which makes them want to pretty much give away their electrons. Non-metals pretty much have all the opposite sort of periodic trends. And double check something here. I'll say. We won't have echo. All right. So the metals, as I mentioned, pretty much have all those trends where when these two get together, we will get a transfer of electrons that's going to happen from the metal to the non-metal. The result of that is it will make a cation for the metal, which is positively charged, and it will make an anion for the non-metal as it picks it up. And that's really, if you just think about sort of the location of those things, non-metals are far right, upper right of the periodic table, really metals left of the periodic table there. They're on very opposite sort of ends. So we get this sort of transfer of electrons that occurs with them. The important thing about an ionic bond is to remember that there is no sharing of electrons here. It is the electrostatic attraction, which again is a fancy way of saying opposites attract. So the positive charge is attracted to the negative charge there. And that's what really holds that unit together. So something like, for example, sodium chloride is an example of an ionic compound. That is a metal and a non-metal. Remember, as we talked about when we did naming, when we do write the formula for anything that is ionic, the actual formula for the ionic compound itself does not have a charge. We want it to equal 0 when you put the positives and negatives together. But they are made up of two things that do have charges. Again, this guy's made up of a sodium ion, and this guy's made up basically of a chloride ion. So, but when we do put them together, simplest way to get to 0 is how we do our ionic sort of formulas, as we talked about. The other type of bonding is really covalent bonding, and covalent bonding is between two nonmetals. And because it is between two nonmetals, they're essentially located at the exact same spot on the periodic table, which means they have very similar properties. And most nonmetals have the properties of they do not want to give away their electrons. In fact, they would like to keep their electrons. They also would like to take other people's electrons and really gain electrons. So nonmetals have all these properties where they pretty much want to hang on to electrons and gain electrons. So the problem arises when two nonmetals get together to make a covalent bond. Neither one of the nonmetals are going to want to give up their electrons. So what happens is the best that they could do is sharing here. So some type of sharing of electrons. And as we'll talk about, the sharing can be equal sharing, or it can be unequal sharing. But there is some aspect of sharing that is going on. And we talked about last time as well using Lewis dot symbols to help us understand bonding, and also sometimes it's referred to as electron dot symbols. And these are basically the symbol with a dot to represent each of the elements' valence electrons, as the valence electrons are the ones that are involved in bonding. Remember that there's no real hard rule on this other than usually not more than 2 per side. And since there's 4 sides, that's 8 electrons, which is a really important number, obviously, in bonding. As we've talked about, I think before, really the whole basis of bonding, both ionic bonding and covalent bonding, is for everybody to achieve noble gas configuration in terms of their electrons. to end up the same electron configuration as a noble gas, which are really, really stable. And obviously, noble gases are group 8 on the periodic table, which is why everybody shoots for 8 electrons when they're doing bonding. The one exception that we probably talked about, and we'll talk about more again, is hydrogen. If you look on the periodic table, hydrogen just needs to get to helium on the periodic table, and helium only has 2 electrons, which means hydrogen should never have more than 2 electrons ever in any situation. It should never, ever, ever, one more time, ever have more than 2 electrons when you are drawing hydrogen. Now, I think we finished up starting to talk about covalent bonding. We showed an example of ionic bonding using Lewis dot symbols, I believe. So, for example, if we had lithium 1s2, 2s1 plus fluorine that has 7 valence electrons, 1s2, 2s2, 2p5, this lithium is going to send it over here to the fluorine. The result of that is when lithium will gain a positive charge, and our fluorine, which has room there in the p subshell for that electron that's coming over, because the p subshell could hold 6, we'll add it there and again sort of complete its octet, gain a negative charge. The end result of this is what I just talked about. The lithium will lose its valence electrons, ends up at 1s2, which is the same electron configuration as helium. Fluorine will gain the electron right there in that p subshell and end up as 1s2, 2s2, 2p6, which is the same electron configuration as neon. So that again is essentially how ionic compounds achieve that noble gas configuration. Metals will lose electrons, and if you look on the periodic table, when they lose electrons, they will back up to the noble gas that comes right before them in terms of their electron configuration. So if you look at lithium, you go backwards there, helium is the noble gas that comes right before it, and it will back up to that noble gas configuration. Nonmetals will actually gain the electrons and go forward on the periodic table to the noble gas that comes after them. So if you look up there, that's fluorine, head 1 forward, that is neon, which is the noble gas that comes after that. Now with covalent bonding, as we talked about before, thank you very much. When we have these two nonmetals coming together, because they will want to share those electrons, that is essentially what happens. And we get the sharing of those electrons between the two atoms. The electrons which are negatively charged are attracted to both the positive nucleus in each of those atoms. And that's what essentially locks those negative electrons in the middle of those two, is it's like attracted to this nucleus, then it's attracted to this nucleus. So it kind of keeps those electrons between the two atoms basically locked in. And it makes a bond, which you could represent with those dots. You could also represent bonding electrons with a line. One line represents 2 dots or a pair of electrons. And what this allows is the hydrogen on the left to get our 2 electrons. And by sharing there, the hydrogen on the right will also achieve the 2 electrons that's necessary for each of the hydrogens to be really stable. And again, basically achieve that noble gas configuration. I think we finished up last time talking about fluorine doing kind of the similar idea here. When you have 2 fluorines, once again, they're going to share those electrons. The result here is we will get some electrons being shared. And those 2 electrons do count for the fluorine on the right, and they will also count for the fluorine on the left. The result of that is, in this case, that gets both of these guys to 8 valence electrons, which makes it really stable. And again, happy in that situation. You also, again, can show the bonding electrons with that line. So it's more commonly sort of represented like this. Remember that these electrons that are involved in a bond are referred to as bonding electrons. All these kind of dots, if you will, that are not involved in bonds. And again, we know they're not involved in bonds because there's no other element on the other side of those electrons. These are what are referred to as non-bonding electrons. Are lone pairs. They're also referred to as well. Any questions on that stuff we talked about, I think, last time there? All right, then let us continue on where we left off. Again, a Lewis structure, as we've been talking about for covalent bonding, shows, again, the bonded atoms and the non-bonding electrons shown as lines for the bonding are dots, and definitely pairs of dots for our non-bonding electrons. Remember that when we are talking about bonding, it is only the valence electrons that are involved. Those are the highest energy electrons, and remember that they equal the group number for each of the groups on the periodic table. So the number of valence electrons is the electrons that are there, which are core electrons, are not involved in bonding. So only the valence electrons are shown in Lewis structures when we look at them. A couple other examples here is water. And again, here, water, just like the F2, by sharing electrons with both of the hydrogens, actually, in this case, that oxygen there is going to achieve 8 electrons. And each of the hydrogens by sharing will get to the 2 that is necessary. And here that will allow water basically to be really happy. Everybody's good. Everybody's met the octet rule in that particular situation. So obviously, the octet rule is really important in bonding. Pretty much everybody will continue to make bonds until they get basically 8 electrons around them. Obviously, as I mentioned a number of times, hydrogen, the exception to that, hydrogen should always be on the outside of the molecule and should only really have 2 electrons going to it. Really, one bond going to hydrogen, and that's all it should have, nothing else. As we will talk about, in order to meet the octet rule, sometimes it does just require single bonds, but sometimes it does require double bonds or triple bonds to meet the octet rule. So with that being said, usually the best approach really is kind of starting with single bonds and really saving double bonds or triple bonds for a situation where the octet rule is not met. Usually it's a really bad idea for people to double bond or triple bond right out of the box. So again, sometimes single bond's all you need, and that would be right there. And again, one line represents a pair of electron or 2 electrons. Sometimes you actually need some double bonds to allow people to reach the octet rule and be happy. In the case of CO2 here, we actually will need not one, but actually 2 double bonds to allow it to get to the octet rule. A double bond is represented by 2 lines, or it is 2 pairs of electron, or 4 total electrons in this case. And lastly here, sometimes it does require a triple bond to achieve that noble gas configuration. And the case of nitrogen actually needs 3 bonds there to do so by sharing electrons here, sharing those 6 electrons along with the 2 on the outside. Each of those nitrogens are able to achieve 8 electrons. Here's a triple bond between carbon and carbon, which is very common. We'll see that guy later when we get to organic, but in order for the carbons, each of those carbons to achieve 8 electrons, it actually will need to make a triple bond in this case. Triple bond is 3 lines, or again, 6 total electrons, or 3 pairs of electrons are used. So again, best approach, as we will talk about, is kind of single bonds, save double bonds or triple bonds for some type of situation where you might need to fix something. Any questions on that there? So what happens if we actually have these electrons being shared? How do we know if, for example, the electrons are going to be shared equally, or they're going to be shared sort of unequally? And really, the overwhelmingly thing that you look at in terms of whether or not electrons in a bond where they're being shared, a covalent bond, will be shared equally or unequally, is electronegativity. And that essentially is the ability of an atom to bring electrons towards itself. I think we might talk about when we talk about some of those trends. It increases as you go up to the right and decreases as you go down. Fluorine is the most electronegative element you could have. So Electronegativity plays a really important role in how those electrons between two atoms within a bond is shared. So for example, if we took our hydrogen there, so since they are both hydrogen, we would expect these electrons to be equally pulled in both directions because hydrogen has the same element, has the same electronegativity, which means they're going to pull those electrons equally. You could kind of think of it like a tug of war, like a rope, and you got like a flag in the middle. And if you have people on both sides of the rope pulling equally, pretty much the flag's just going to kind of stay in the middle, right? So that's sort of the idea here. We're going to have an equal pool of those electrons. That's going to result in those electrons being shared equally. Same thing if we looked at our fluorine in this case. Between the two fluorines, they will also share the electrons equally. In a situation where we have equal sharing of electrons, that is what is known as a nonpolar covalent bond. Most people just call it a nonpolar bond these days to kind of leave the covalent off. It's assumed that there's sharing of electrons. So whenever you have equal sharing of electrons, it's considered nonpolar, the bond. That means that those electrons are sort of spread out equally and shared equally over the bond. The result of that is what type of bond you actually create is, if you want to think of it this way, is like a neutral bond. It's like no side's more positive, no side's more negative. It's like nice and everybody's just kind of equally sharing those electrons in this situation. Now, what would happen if we took something like HF? So we swapped out one of those fluorines for a hydrogen. Now, between hydrogen and fluorine, with fluorine being the most electronegative element you could have, between hydrogen and fluorine, where should the electrons head towards? It should head towards the fluorine because it is the most electronegative. Electronegativity, again, is the ability to bring electrons towards itself. So because there is now a difference in electronegativity, what's going to happen is these electrons here in this bond are going to kind of start heading, if this little scribble here is the electron density, and kind of head a lot more closer to the fluorine side than the hydrogen side in the bond. And that's going to cause a situation to occur where if all the electrons are sort of heading towards the fluorine side, would we expect the fluorine side to be more positive or more negative in this case? It would be more negative because those negatively charged electrons are hanging out over there. And what that creates on the fluorine side is a partially negative charge and a partially positive charge. Those are delta symbols, delta negative, delta positive. Partial charges occur within this bond. We could also represent this another way in bonding, which is very common. We could use what is sometimes referred to as a dipole arrow. Use this like dipole arrow. And the dipole arrow always points to the more electronegative side. And the back part of the arrow that kind of makes like a plus sign is to the more positive side of the bond. Why in this case is the bond between hydrogen and fluorine only creating partially negative charges and partially positive charges? Why are they not creating like full positives and full negative charges? The answer is these electrons are still being shared, right? So they are still being shared here. They're being shared unequally, but there is some aspect of sharing, which means the hydrogen hasn't completely let go of its electrons. He's like, if you want the tug of war example, he's still barely hanging onto the rope. He's just getting dragged across the cement or the dirt there, but he's still hanging on. So the electrons haven't fully transferred like what we see in an ionic compound. In an ionic compound, when the metal and non-metal get together, there is such a difference in like those properties that the electrons jump from the metal to the non-metal, and we get a full positive charge on the metal, making a cation. a full negative charge on the nonmetal, making an anion. But here there is still some aspect of sharing happening, which is why we only get these partially positive and partially negative charges. This type of bond is what is referred to as a polar covalent bond, or just a polar bond, most people call it these days. And that is a result of unequal sharing of electrons. Question on that there. My little smear there. So if you sort of think about the three sort of types of bonding that we talked about, on one end of the spectrum, you have ionic bonds, which is always between a metal and a nonmetal. And in that case, as we talked about, we are going to get that transfer of electrons, creating fully charged ions like cations and anions. Again, no sharing of electrons. And an example would be sodium chloride. On the other end of the extreme, we have a nonpolar covalent bond. And that's between two nonmetals which share very similar periodic trends, which again means neither one of them want to really give up their electrons. And what the result of that is, we will end up with equal sharing of electrons. Like a couple of those that we saw, H2, F2 are examples of that. And sort of in the middle of the two is a polar covalent bond. Also between two nonmetals. And here we have unequal sharing of electrons, resulting in these partially positive, partially negative. These sort of charged bonds where there's a like positive side to the bond and negative side to the bond is actually really important, as we'll talk about in later chapters, of why certain things are able to interact well with other things and why certain things are not able to interact really well with other things as well, having these polar bonds or not. So one end of the extreme, we get a complete transfer of electrons in our ionic bonding. Other end of the extreme, nice, perfect, equal sharing. And in the middle, we get not equal sharing, but not so unequal that the electrons jump ship, but we get this unequal sharing that occurs in our polar bond. Any questions of those three there? Go. So as I mentioned, electronegativity really is the overwhelming thing that we look at. Extra there, I suppose. In terms of whether or not these electrons are going to be shared equally or not. It's related to electron affinity and ionization energy. Remember, ionization energy is the energy required to remove an electron, and electron affinity is the energy change that occurs when somebody gains an electron. And fluorine has high electron affinity, which means it likes to gain electrons, and it has high ionization energy, which means it does not like to give away its electrons. It takes a lot of energy to try to remove an electron. And sodium, on the other hand, has low electron affinity. It's not looking to gain electrons and has low ionization energy, which means you could pretty much just give away its electron pretty easily. It's not going to put up much of a fight in that particular case. Now, how do we know if a bond's going to really be sort of polar or non-polar or even ionic? We could use the trend in electronegativity, which again increases as you go up to the right on the periodic table and decreases as you go down. A guy by the name of Pauling actually came up with values for electronegativity, and these values run from 0 to 4. 4 is the most electronegative element, 0 not so much, right? So you could actually calculate, if you have the values, what is referred to sometimes as delta En, which is the change in electronegativity values. And if you calculate the change in electronegativity values, which is simply just taking the two electronegativity values within the bond and just subtract them, larger from smaller, so you get a positive number. And if you get anywhere from 0 to 0.4, that bond is considered really a nonpolar bond. We're going to have some equal sharing of electrons that's going to happen in this case. If you got above 0.4, which I guess would be 0.5, and you are below 2, you will have some type of polar covalent bond, which means we will have unequal sharing of electrons in this case. So equal sharing, unequal sharing. And not in all cases, but typically above 2, there are some exceptions, you would have an ionic bond. No sharing, right? Transfer of electrons. Now, the truth be told is you absolutely positively do not even need these values for ionic bonds, because as soon as you see a metal and a non-metal, it's ionic. Don't even worry about it. Yeah. So you can identify these two things as a metal and non-metal. It's going to be an ionic bond. You had a transfer of electrons. I wouldn't even worry about it. I would use electronegativity values mostly for these two to determine whether or not you got a polar bond or a non-polar bond. By the way, typically speaking, another terminology is sometimes used if you have an electronegativity value of exactly 0, that is like as perfect equal sharing as you could get, is sometimes also referred to as a pure covalent bond. And that is still a nonpolar bond. But sometimes people will specify that you got that perfect equal sharing, so it's a pure covalent bond, as equal sharing as possible. So here's a table of electronegativity values, and you can see it increases as we go up to the right, with fluorine being the most, decreases as you go down and to the left. Here's another value. Here's another one in case. So we'll take a look at this one. It's got a few more numbers. But if we look at, for example, our ones that we did previously, go here. We had our sodium chloride. We had our HF bond, and we had our F2 bond, right? So how we would use these values here, and obviously they would be provided for you if you needed them, we would just look up the values. So sodium here is 0.9, chlorine here is 3, and what we're going to do is just subtract the two numbers. We're going to take the larger number minus the smaller number, and that's going to give us 2.1. 2.1 is above 2, which would tell us it's ionic, but once again, you really don't need it because you have a metal and a non-metal, so it should be ionic. The reason I say you should just go with metal, non-metal, it's going to be ionic, is because you definitely could have a difference less than 2 and still be ionic. Like, for example, if I took lithium, which is 1, and bromine, which is 2.8, and I subtract that, 2.8 minus 1 is 1.8, which is less than 2, but is still an ionic compound. So the 2 rule for ionic isn't like perfect number. There definitely is a lot of ionic bonds where if you take the differences, you will get less than 2. So again, for ionic, it's best just to go with metal, non-metal is going to be ionic. Not even worry about the numbers. If we take our fluorine here, that's a value of 4, and fluorine has a value of 4. So if we take the difference in electronegativity, 4 minus 4, that is as perfect equal sharing as you could get. That's going to be a nonpolar bond, as that is less than 0.4, obviously. And if we look at hydrogen here, which is 2.1, and fluorine, which is 4, do the difference in electronegativity, 4 minus 2.1 is 1.9, yeah? And that will definitely be above 0.4, but less than 2, and that would be a polar bond. That is almost to the 2 limit there. That's super unequal sharing of electrons. Those electrons are really always kind of really close to the fluorine, but again, the hydrogen is still hanging on, so there is still some type of sharing of those electrons. By the way, for anything that is polar, we could draw that bond dipole arrow, again pointing to the one that is more electronegative in the bond. And again, it would look something like that. We would not use that arrow for a nonpolar bond because there is no negative or positive side. It's equal sharing of electrons, so kind of like a neutral bond in that case. Question on how to do that there. So why don't you try some here? We'll go with this guy here. Why don't you do carbon oxygen bond, sulfur oxygen bond. We'll do carbon hydrogen. We'll do yep, lithium fluoride, and then why don't we do carbon and sulfur? So for each of these, use the electronegativity values to decide, is it ionic, is it a polar bond, or is it a non-polar bond? So calculate the difference in electronegativity values there for each of those. And again, I'll put the breakdown for you again. 0 to 0.4, non-polar. Basically 0.5 to less than 2 is polar. And above 2, ionic. All right, so take a moment there, see what you come up with. All right, so let's take a look. So again, we'll start on the left here. Lithium is 1 on the table. Fluorine is 4. So again, we're just going to take larger number minus smaller so we don't get a negative number, which is going to give us 3. And that definitely means that it should be ionic. It's above 2. We once again don't really need the values here because lithium's a metal, fluorine's a non-metal. So we should just know right from that jump there that it is basically going to be ionic. We come up here to carbon oxygen. Carbon is 2.5. Oxygen is 3.5. Thank you. Difference in electronegativity there going to be 3.5 minus 2.5, which will be 1. 1 is above 0.5, but less than 2. So this tells us it's going to be a polar bond. That means we're going to have unequal sharing of electrons. And if I were to draw that arrow, it should point to which one, carbon or oxygen? Should point to oxygen, which is the more electronegative element there in that bond. That means the oxygen here will be more partially negative. The carbon here will be more partially positive because of that unequal sharing of electrons that's occurring. If we go to sulfur there, which is 2.5 still. There we go. And our oxygen, which is also 3.5. We are going to get the same calculation right there, and we will get a difference of 1 in this case as well. And that will tell us that this guy will also be polar. And once again, here our arrow should point towards the oxygen in this case, as it's being more electronegative. We come down to carbon and hydrogen. Carbon being 2.5, hydrogen being 2.1. Difference in electronegativity, 2.5 minus 2.1, that's 0.4. This is going to be what's a bond? It is going to be a non-polar bond. Also, why the cutoff is at 0.4, because that is the bond that you see the most in organic molecules, which are non-polar compounds, and that carbon-hydrogen bond is considered non-polar. Is it a perfect equal sharing of electrons here? It's not. It's just slightly heading towards carbon, but not enough to be considered a polar bond. So still considered a neutral bond in this case. Lastly here, carbon at our 2.5, our sulfur at our 2.5. That's a difference in electronegativity of 0, I believe, right? That's going to make this a non-polar bond, right? So we're going to have equal sharing of electrons. I should go down here. Non-polar, right? That's going to be a non-polar bond. Again, that's like a pure covalent bond, actually. Perfect equal sharing of electrons in this particular case. Any questions on how to use electronegativity? So this also brings up a good point that you definitely can have 2 different elements that share the same electronegativity values. This is what is sometimes referred to as the diagonal relationship on the periodic table. Carbon is further up, but sulfur is further to the right. They cancel out their differences diagonally there. Not perfect diagonally, kind of diagonal over a little bit there to the right. And they will have that. There's a lot of places or a few other places where that occurs. For example, nitrogen and chlorine, also diagonal of each other, has the same electronegativity value. So there are a few that are diagonal of each other that will have the same electronegativity values, which will create actually a non-polar bond. So definitely possible to have different elements that will end up sharing the electrons equally. Definitely for sure, if it's the same elements sharing the electrons, going to be equal sharing of electrons, because it should definitely be a nonpolar bond. Question on that there. Now, do you always need the values? The answer is no, you really don't always need the values. In a lot of cases, you really don't actually need them very much. Especially if you have, for example, like we had here, that's carbon and oxygen. They are in the same row or period on the periodic table, right? Oxygen is further to the right, which means it should be more electronegative, and that should create row. And they are different spots in the same row. It will probably create if you're non-metals together. By the way, if we look at sulfur and oxygen, which is another one here, they're actually in the same group on the periodic table. Oxygen is further up than sulfur, which means oxygen should be more electronegative and will create a polar bond. So if you're comparing something that's in the same row on the periodic table and are the same group on the periodic table, you really don't even need the values. You could probably make a pretty educated guess that it will make a polar bond if that's the situation in that case. So a lot of times you can make a pretty good guess just with the general trend without the numbers of whether or not you would expect a polar bond, especially if you're comparing something in the same row or same group. Any questions on that there? Again, just that diagonal relationship, you just got to kind of watch out for a little bit as you go do it. All right, so obviously, as we saw there, atoms with really widely negativity values will create really some type of ionic bond if they're going to be really, really different, or some type of polar bond. And ones with equal sort of sharing there will get you your nonpolar. So here's sort of that breakdown that we talked about in terms of difference in electronegativity values. So now that we know sort of what determines how those electrons are going to be shared, let us talk about the steps in drawing Lewis structures for covalent molecules. And if you follow these steps, you should end up with a pretty good picture when it's all said and done. I would not do any type of piecework, which is just kind of putting everything together individually and try to figure out how they come together. So the first thing that you want to think about is when you're drawing a Lewis structure for covalent bonding, where things are going to be sharing electrons, you want to think about how is the thing sort of put together. And to help you make your decision, a lot of times there is a central atom and there's stuff that's just basically attached to the central atom. So they're all just kind of attached there to the central atom. What should usually go in the center is the least electronegative element, and you should never have hydrogen in the center, and you should never have fluorine in the center, because if hydrogen's in the center, it's going to have way more than 2 electrons, and that's going to give you an X that you don't want. And if you put fluorine in the center, fluorine is the most electronegative element, so it should never be in the center. So those guys should always usually be on the outside. Once you figure out sort of how it's arranged, and it's a lot of times just logically thinking, if you have like one element and like 3 of something else, usually the one guy's in the middle and everybody's just kind of directly attached to it. The most important thing when you go draw Lewis structures is the total number of valence electrons. So that's in the entire molecule or ion. Again, number of valence electrons equals the group number. So we're just going to add up all the parts that we're going to draw and add up all the valence electrons. If it is some type of polyatomic ion that you're drawing, you do have to take the charge into account when you count up your valence electrons. So if something has a negative charge, we're going to add some electrons to the total, whatever the charge is. So if it has a -2 charge, you would add 2 more electrons to your total. If something has a positive charge, the way femtoguess becomes positive is it loses electrons. So you will subtract that positive charge from your total. So if you had a +1 charge, you would subtract 1 electron from your total. So that's really important. This number is really important because, frankly, when your picture is done, that's exactly the number of electrons your picture has to have. Cannot have any more, cannot have any less. It needs to hit right on that nose and that number. You should also think of these electrons as not belonging to anybody. And that's where people get in trouble is they try to do piecework like, okay, nitrogen's got 5, so it needs 3 to get to 8. And all of a sudden they're trying to figure out how it does that. And a lot of times when people try to do that kind of piecework, you end up with too many bonds, not the right number of bonds, and not enough electrons and stuff like that. So the idea here is you want to think of these electrons as belonging to everybody. And what we want to try to do is just equally distribute those electrons to everybody involved in the structure. And the way that we do that is the first thing that we want to do is draw one single bond from the center atom to each of the outside atoms. So I use lines for bonds. So you can use lines. If you want to use dots, you can still use dots if you like. But one line to every outside atom. Each line represents how many electrons? 2, right? So each line will represent 2 electrons. So you're going to count up how many electrons you use to do that. And all the remaining electrons will go on the outside atoms in pairs of electrons. So they'll go in as dots around all the outside atoms until each outside atom has 8 electrons, unless it's hydrogen, then it won't have any, up 2. And then if you filled up all the outside atoms with electrons and you still have electrons to go, then you go to the center atom and you put them on as dots of electrons or pairs of electrons onto the center atom. At that point, once you're putting pairs of electrons on the central atom, you should be done and out of electrons. If you're not, something's probably wrong. The last thing that you want to think about is, did everybody meet the octet rule? And it's at that point where you've already distributed all your electrons. If somebody has not met the octet rule, then you should try to fix that by making a double bond and exhaust all your double bond possibilities. And if that still doesn't work, then you should go to triple bond. Once again, you should not double bond or triple bond right out of the box. It's usually not a great idea. That's a lot of words. Let's see how it all works, right? So NF3. So we're going to draw this here. So nitrogen is group 5, which means it has 5 valence electrons. There are 3 fluorines. And fluorine is group 7. So that is 26 valence electrons. So my picture should have 26 valence electrons in this case. Between nitrogen and fluorine, nitrogen is the least electronegative atom or element. So we're going to put that guy in the middle. We're going to put the fluorines around. And to answer your question, it doesn't matter. You can put the fluorine in the bottom like I did, or you can put the fluorine up on top if you like. It doesn't really matter. Once I have my logical arrangement, I'm going to do just a single bond to everybody. And at that point, I now put on there 2, 4, 6 electrons, 2 for each line that's there. If I subtract that off, that is 20 more electrons I have to go. Those 20 electrons are going to go on the outside atoms in pairs of electrons. So here we go. We got 2, 4, 6, 8, 10, 12, 14, 16, and 18 electrons I just put on there. Still got 2 to go, by the way. I stopped at each of those because each of the outside atoms now have 8 electrons total, right? Each of them have 8. So 2, 4, 6, 8 for each of the fluorines. I still have 2 to go. I then go to the center atom, and it goes on as dots, just like so. I have now placed all 26 of my electrons. The last thing I want to make sure is everybody there has 8 valence electrons. So 2, 4, 6, 8. All the fluorines are identical. 2, 4, 6, 8. 2, 4, 6, 8. Nitrogen, 2, 4, 6, and 8 underneath. Everybody has 8 electrons. There's only 26 electrons on that picture. And everybody's happy with single bonds. No need for double bonds or funny looking things because it looks more chemistry like. Yes. Any questions on that there? All right. Why don't you try one here? Why don't you try this one, NO3 minus, and draw that, see what you come up with. Okay, so let's take a look at this one. Again, we're going to do the same thing. I got 5 for the nitrogen. There are 3 oxygens. Each is group 6. -1 means it has gained electrons, so I need to add that 1 into my total. Otherwise, I'm going to be off. So I got to take that charge into account here. 18, 19, 24 valence electrons. Again, if you look on the periodic table, nitrogen and oxygen are right next door to each other. And oxygen is further to the right, which means it's more electronegative. So our nitrogen should be in the middle. Oxygen should be around. We're going to do our same thing here, a single bond to everybody. That is, again, 2, 4, 6 electrons. A lot of math, we'll go 18. So we have 18 electrons to go. Again, we're going to work outside in with dots, pairs of electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18. At this point, I have no more electrons put up on my picture. Is everybody good in this case? The answer is not so much. So oxygen is good. We got 2, 4, 6, 8. All the oxygens are the same, right? Nitrogen, though, has how many? 2, 4, 6. A little short. So it is actually short here. And this is the part where we want to try to fix it. So can I just put some dots there? I cannot, because now how many electrons do I have? 20 too many, 26, I think, right? So I have too many electrons. So this is a case where this is where we want to make a double bond to fix it. Can I just lay a double bond in, like, say, there? I cannot, for the same reason. I now have 26 electrons still. The oxygen up on top now has 2, 4, 6, 8, 10 electrons. Too many. So when we make a double bond, which in this particular case, you could actually do it at any of the oxygens, they're all the same. We are actually need to take a pair of electrons, these two, let's say right there, and we're going to bring them in to make the double bond. So we're going to take a pair of electrons from the outside, bring them in to make the double bond. The result of that in this case is we will end up with a double bond up on top, and we will still have our single bond on the sides here. And we'll put a little bracket on it with a negative on the outside since it has a charge, makes it look nice. We now still only have a total of 24 electrons. The nitrogen now is good. It has 8. Let's put little circles, 2, 4, 6, and 8. Each of the oxygens have 8, and even the double bonded oxygen, 2, 4, 6, and 8, basically electrons. So this is perfectly good in this case. Question on that. So when we make a double bond, we actually have to bring a pair of electrons in to make the double bond. By the way, when you make a triple bond, you do the same thing. You got to bring a pair of electrons in to make that triple bond as well. We could have double bonded to the right in this case, and that would have gave us a single bond up on top, a double bond on the right. We also could have double bonded on the left there, would have gave us a double bond on the left. Single bond up on top, single bond on the right. All 3 of these structures are related to each other. This is what is known as a resonance structure. That is because those double bond electrons are frankly delocalized. They're just moving around. And what I mean by that is if you just kind of look like this, at any given point in time, those double bond electrons that we sort of brought in to make the double bond could be over here, but then they could be up here, they could be over there. They're just kind of moving around from one spot to the next. So you could actually draw 3 equivalent Lewis structures, which are known as resonance structures. Resonance structures usually have these arrows between them to indicate it. And that's because one structure by itself really doesn't adequately describe what's going on here in terms of those electrons. But you could draw any one of the 3 pictures if you were just asked to draw the Lewis structure. You don't have to draw all 3 of them unless you're asked to draw the resonance structures. If you're just asked to draw a Lewis structure, you could have laid up any one of the 3 pictures and it would have been fine. Any questions on that there? All right, so let's try a few more here. Just make sure. Why don't you do why don't you do carbonate? Why don't you do SO2? Why don't you do CO2? Okay, so let's take a look, see how we're doing on some of these. We'll start here. We got 4 for the carbon and 3 times 6 for the oxygen. Once again, -2 means we need to add 2. So it's 18, 20, 24. Here, carbon is going to go in the center, oxygen around. We're going to do our single bond to everybody. That's going to use up 2, 4, 6 electrons. The rest are going to go on the outside. So 2, 4, 6, 8, 10, 12, 14, 16, 18. At this point, we have now placed all 24 electrons. Is everybody okay in this case? Carbon is not good because it only has 6, right? 2, 4, and 6. It is short. All the oxygens are okay. So remember, everybody needs to get to 8 except for hydrogen. So again, here we can make a double bond just like the nitrate. You could actually do it at any of the oxygens. So if we take a pair of electrons in, that will give us a double bonded oxygen up on top. And again, we'll put our little kind of charge on it in a bracket. This is another one that could be a resin structure where it's perfectly fine if you double bond it over to the left. And also you could draw one more where, yeah, let's go this way with it, where you could double bond it to the right. You can see a resin structure really is, for the lack of a better description, just move the double bond to all the possible locations and you can draw a new structure basically in this case. Any questions on that one there? Coming over here, sulfur is 6 plus 2 times 6 for the oxygen. That's 12, 18 valence electrons. In the middle should go the sulfur. Oxygen on the outside, so we'll just go side by side. Going to do a single bond to each, so that is 2, 4 electrons. That leaves me 14 more to go. That's on the outside first. So 2, 4, 6, 8, 10, 12. I still have 2 more to go. They actually do go to the center as dots. That is how they get there. Not like a lot of people will draw this one double bonded on both sides incorrectly. So they do need to have dots here. Bless you. At this point, when we look at it, hopefully you can see that sulfur, in this case, is not good. Oxygen's okay on both sides. They have 8, but sulfur has 2, 4, and 6 only, so it is short. Here we could actually make a double bond on either side. So I'll go left first, so I can bring the electrons in to do that. And when I do that, that will turn my double bond to the left here. Still have the dots up there on the sulfur. Also another one that you could draw a resin structure because you could have double bonded to the right instead. Perfectly okay if you did it this way. Any questions on either of those there? Again, you should hopefully see I'm following the pattern there of how to do it. I'm not double bonding or triple bonding out of the box. Again, saving that to fix something is the best approach. Any questions on that there? Coming to my next one, which is CO2. 4 for the carbon, 2 times 6 for the oxygen, 12, 16. In this case, carbon's going to be in the middle. Oxygen will be on the outsides. Single bond, that is 4 electrons. That means I got 12 more to go. That is 2, 4, 6, 8, 10, and 12. Is everybody good in this case? Which one is not good? Carbon. So here we could double bond left or right. So we could take a pair of electrons in, and that will give us our double bonded oxygen. Did that double bond fix the situation? No, it got better, right? And now it has 2, 4, 6 electrons. Now, again, here, we actually have an option to double bond on the right-hand side. And you would want to do that in this case before you went to triple bond. So you kind of want to exhaust all your double bond possibilities before you jump to that triple bond for reasons outside of our class. Why that's a good idea. But we would do the same thing to double bond the other side. We're going to bring those electrons in to do so. That will give us a double bond actually on both sides. Now we have a grand total of 16 electrons, and everybody has 8 electrons around it. Again, you can count the dots, the lines, they all count as electrons, and everybody has 8. Any questions on that one there? So in this case, again, required 2 double bonds to get there. Here we have 5 plus 4 times 1 for the hydrogen. I'm going to subtract 1 because of the positive charge. That's going to give me 8 valence electrons in this case. Nitrogen's going to go in the middle because we would never, ever, ever put hydrogen in the middle, right? Because we do not want an X on our paper, right? We're going to do something like that. We're going to go with a single bond to everybody. 2, 4, 6, 8. I'm out of electrons. I'm actually good in this case as well. Hydrogen only needs 2, right? So it's good, and that's what hydrogen should always look like. No dots, no double bonding, no triple bonding, no triple bonding and dots for good measure. So just look like that, basically, yeah. Any question on that one? Lastly here, our N2, which is nitrogen. And that is basically 2 times 5, which is 10 valence electrons. There really is no central atom here, so you just go side by side. And you can still do the same method, which is connect them with 1 bond. That is 2 electrons. 4, 6, 8, 10. Doesn't really matter which nitrogen you put the dots on to start with. At this point, nitrogen on the left is a little short, right? It only has 4 electrons. Nitrogen on the right is actually good. So we're going to double bond it by bringing this in. And that's going to give us a double bonded nitrogen. That means the nitrogen on the left is actually still short in this case, right? It's got 6 electrons. Nitrogen on the right still has 8. I have no more opportunity for double bonds, so now we're going to triple bond it. Same deal, going to take a pair of electrons in to make the triple bond, and that's going to give us a triple bond in this case. And now we have 8 electrons for both nitrogens, and only a total of 10 electrons, which is how nitrogen gets to a triple bond, by the way. Any questions on how to draw Lewis structures? So you definitely want to follow these steps. It should lead you to a pretty good structure. Again, avoid the trap of I just want a double bond or triple bond out of the box. Just follow those steps and you should kind of get there. Any questions on any of that there? Yeah.
SO2 with the electrons over the X versus with CO2. You didn't put the electrons over the CO2.
I didn't put the electrons on the CO2 because I was out of electrons with the CO2 at that point. I had placed all CO2 had 16 electrons. At that point, I had 2, 4, 6, 8, 10, 12, 14, 16. I had no more electrons to put on the center atom. So we work outside in, right? When I went to SO2, I had 18 electrons. I had 2, 4, 6, 8, 10, 12, 14, 16. I had 2 more electrons I had to place, and that is how we got to those 2 that go on the center atom. So you again do not want to move into, trust me when I tell you, do not want to move into double bond or triple bond territory. I feel like we're playing football, but you don't want to do that until you've distributed all your electrons as dots. So you want to always go in that order. Single bond everybody, outside dots and pairs until the inside dots if necessary. At that point, no more dots. Then you want to look and make sure everybody's good. And if somebody's not good at that point, you want to double bond or triple bond. And in the case of the CO2, we were out of electrons by the time we were done with the outside atom. So we had nothing to put on the central atom. Other questions? So we talked a little about resonance structure, but let's talk a little about bond length here, and you don't have to memorize these numbers, but when we look at these numbers, what we do see is a pattern in terms of bond length. This is the carbon-carbon single bond, 154, carbon double bond, 133, carbon-carbon triple bond, 120. When we look at the carbon-nitrogen single bond, 143, the distance between the two atoms, carbon-nitrogen double bond, 138, and 116 for triple. What we actually see is every time you throw on a bond, the atoms actually get closer together. Yeah. You throw on a double bond, they move closer. Throw on a triple bond, they move closer. Why is that? When you make a double bond or a triple bond, what are we moving in between those two guys to make it? We need to move in electrons, which are negatively charged, right? So now you're building up this bigger negative charge between the two nucleuses, which are positively charged. And what that does is brings everybody in, right? Opposites attract. So single bond is longer than a double bond is longer than a triple bond. They are not like twice as long or 3 times as long, but that's the general trend. That also relates to strength. A single bond is the weakest. A double is the next weakest. All right, sorry, the double bond is stronger than a single bond, and a triple bond is the strongest of all of them. So if you think about it like a brand new pencil out of the box, nice and long, you could take that thing and snap it all day, right? No problem. You take that same pencil, take a chemistry test, and you're left with like a nubbin and an eraser, right? Like that big left, perhaps. Very hard to try to break that thing, right? Everything's really tight together. It's very small, and it's very hard to try to break that. And that's sort of what happens with bonds. As everybody moves in tighter and tighter to each other, everybody's held a lot tighter, makes it a lot harder to kind of break that bond than if they're kind of at a farther distance from each other. The strength of those opposites attract, is based on distance as well. So the farther things are from each other, they're not going to be held as tightly. And that's why, again, a single bond is weaker than a triple bond, and a double bond's between the two. So we talked about resonance structures, so we won't spend a lot of time on it, but again, essentially the idea of resonance structures is those double bond electrons are delocalized, which means they could really be at any point where you have a possibility to make the double bond. So you just want to kind of draw another Lewis structure where the double bond is moved to all the possible ways, like we looked at with carbonate and also nitrate in that case. There was our carbonate example. Again, don't worry about the charges on it. But again, we could have a double bond up here. We could have a double bond over here or a double bond over here. And it's the same idea as what we talked about with nitrate. Those double bond electrons are really just kind of moving around from oxygen to oxygen. So at any given point in time, they could be at any oxygen, which allows you really to double bond any of the oxygens as they're sort of equivalent to each other. Benzene ring, which is sort of cut off there, we will see a little later on when we hit organic for sure. It is a 6-carbon ring that has 3 double bonds in it. That's a carbon, a carbon, a carbon, a carbon, a carbon, and a carbon at each of those spots. A lot of times, as we will see it in our book drawn, because those electrons are moving around, they'll just draw a circle in the middle to indicate those electrons are basically just kind of moving around in any spot. But it does have 3 double bonds at any given time. So let's talk a little bit about some exceptions to the octet rule, although we will not have any exceptions to the octet rule that you'll need to draw or anything like that. But you do need to know what the 3 exceptions to the octet rule are, if that makes sense. The first exception to the octet rule is what's known as an incomplete octet. There are certain elements that are perfectly fine with less than 8 around them. Your most common ones are beryllium, aluminum, and boron. And I would say out of those, boron is typically the one that you see the most. Boron is perfectly fine with 6. That's why it's referred to as an incomplete octet. It is actually what is known as being electron deficient because it's missing some electrons. It actually makes it a Lewis acid, which is a very reactive type of compound. Beryllium and aluminum probably won't see too much. Boron is a very common sort of one of an incomplete octet. Again, we will not have incomplete octets here, but that is one exception to the octet rule. Another couple of exceptions to the octet rule are an odd number of electrons. So that's a situation like NO or NO2. If you count up the valence electrons in NO, that is 5 and 6, which is 11. So that's an odd number. What that ends up being is we will have one unpaired electron. That is sometimes referred to as a free radical. Perhaps you've heard of that. Free radicals are molecules that have one unpaired electron. They happen a lot in atmospheric chemistry with chlorine. They are very, very reactive because, frankly, they are missing an electron, so they want to kind of fix that. So they're very, very reactive type of compounds. So that's another exception to the octet rule, which you will never have to draw in here, either of those. The last one is the expanded octet. And the expanded octet can happen where an atom can actually have more than 8. It could actually go like 10 or 12 around it. And it happens on the periodic table right where you find sulfur, to the right, to the left, and down. And sulfur on the periodic table is period number 3. That is an N equals 3 value, right? When we talk about electron configuration, what orbital appears on the third energy level? First appears on the third energy level is, there are S's, there are P's, and that is where the d orbitals first start to appear. Even though they may not be using those d orbitals, they are available to them to stash all the extra electrons. And that's why those guys can go above 8. That also means that if you go above them on the periodic table, nitrogen, oxygen, fluorine, that is N equals 2. The second period, on the second energy level, there's S and only P orbitals. They do not have d orbitals available to them, which means they can never, ever, ever go above 8. They got to stick to 8 only. So SF6, for example, is an example of that. I'll just quickly sketch. I won't put all the dots on the fluorines, but they all have dots to make them 8. And like so, sulfur has 2, 4, 6, 8, 10, 12 electrons around it. We will not draw anything that is an expanded octet. Yeah, but it can be drawn. So for example, when you go Google something, don't do that. Yes, because they'll know you did it, because you'll come up with sulfate that looks something like this. And I just told you not to draw the expanded octet, and you did that, so it makes me think you looked it up, right? So don't do those things. Yeah? So if you follow our rules, when you draw sulfate, it should look something like that with all the dots on the oxygen, single bonded. And that's what you should do in this class. I will say if you Google it, you'll see the guy on the left, because for other reasons outside this class, the structure on the left is actually a better structure than the single bonded one, but you should follow the single bonded one in here. So these are the 3 exceptions to the octet rule. Do not, you will not have to draw any of these exceptions, but you just need to know what they are. Okay, so everything that we draw in here, you should draw to obey the octet rule. So everything here will obey the octet rule. Any questions on that there? All right. So let's talk a little bit about geometry and molecular geometry. And when we talk about geometry, we could kind of predict geometry from a Lewis structure and really the central atom. And what is it attached to the central atom? How many bonds it has? How many electron pairs there are around the central atom? Now, we're going to talk about geometry. And the basis of this approach is the valence shell repel one another, which means, frankly, when we have bonds and we make bonds and we draw Lewis structures, it's all about electrons, which are all negatively charged, which means electrons will be near electrons, and negatively charged electrons near other negatively charged electrons. Do they really want to be near each other? The answer is no, because they have the same charge. So what happens is, in all situations, the electrons try to get as far away as they can from each other, but they can't escape because they're in a bond, so they can't really escape the molecule. But they will try to move around as far as possible. That makes them happy, makes them good in terms of energy, and that is what gives us these different shapes that we see with molecules based on those electrons moving. We're going to talk about two types of geometry. One is what is known as the electron pair geometry. The electron pair geometry I will just abbreviate as EP. And that is how the electrons around the central atom are arranged in three-dimensional space. There's also the molecular geometry name. That is also sometimes referred to as the shape. And I'll just abbreviate that in this rest of the lecture here as MG. So write it so much. That describes the overall molecule with all its bonds, basically what the shape of it is. So these are names that describe sort of the shapes of these things. And in some cases, what we will see is these names will be the same. And in other cases, these names will be different depending on what electrons are present. So let's talk a little bit about how we do this. This is VSEPR, which stands for Valence Shell Electron Pair Repulsion Model, which is why the abbreviation is there. So we basically will break up molecules into two types. One where the central atom has no lone pairs. So basically you draw the Lewis structure, there's no dots on the central atom. When you're doing geometry, it is all about the central atom. If there's a central atom, it's the only one that's important, basically the guy in the middle. Also, we will do ones where you will draw the Lewis structure and there will be dots around the central atom. So either dots or no dots, basically. When you're doing geometry, and only when you're doing geometry, there are a couple rules that are really important. If you have a single bond, if you have a double bond, if you have a triple bond, so one line, two lines, three lines, it doesn't matter. They all count as one electron pair and one bond. So it doesn't really matter if you got a double bond, triple bond, single bond, you got dots, everybody counts as one, basically. One. That's because in a double bond or triple bond, all those electrons, they're basically just kind of moving in terms of the geometry as one, basically. They're moving around as one unit. The second one is not super important for us, but if you draw any of those resonance structures, for example, you could do this geometry to all the resonance structures that you drew, and you most likely will hit the same geometry for every resonance structure that you drew. So they'll all be the same. All right, so let's talk about how we do this. We're going to start with guys with no lone pairs. So the simplest arrangement, if you don't like all the X's and stuff, don't even worry about it. Well, just listen to what I'm saying. So the simplest geometry that you could have is a diatomic molecule. A diatomic molecule is basically just two things, right? Two atoms. The only way you can arrange two things is a straight line, right? The shortest distance between 2 points is a straight line. The geometry will always be linear. It does not matter if it is a single bond. It does not matter if it is a double bond. It does not matter if it is a triple bond. Does not matter if it is the same thing or different things attached. If you have two, it is going to be a straight line at the end of a straight line, and it's always going to be linear. So doesn't matter. Again, like I said, different elements, same elements, single bond, double bond, triple bond. If you have a diatomic molecule, the geometry of that will be linear, again, arranged in a straight line. When we get three or more atoms involved, you do have to look at a couple of things, and those things are how many electron pairs there are and how many bonds. Again, the central atom is the most important thing. In a case like this, where there's diatomic molecules, there is no central atom. There's only two, right? So you can't have somebody in the middle, right, of two. So if there's only two things, there really is no central atom. But when you have three or more, you will have always like an atom in the middle. And that, when you're doing geometry, again, is the one that you want to look at. So let's take a look at some of those and see what we're talking about. First example here, an exception to the octet rule. So what we want to look at here when we look at this guy, BeCl2, We want to focus in on the central atom here, and that is the most important thing. Here are the two things that we want to know. The number of electron pairs. It doesn't matter if they are single bonded, double bonded, triple bonded. Doesn't matter if they're dots. How many electron pairs are around that central atom? There is 1 and 2. Yeah. So 2 electron pairs. Something with 2 electron pairs. The electron pair geometry name is what is known as linear. What's going to happen is those 2 electron pairs are going to try to get as far away as they can from each other. So they end up going on opposite sides of the center guy. And that is going to make them basically a straight line, which is why it's linear. Because they have bonds as well, the number of bonds in this case is how many? It is also 2. 1 bond, 2 bonds, right? So something with 2 electron pairs and 2 bonds will have a molecular geometry or shape, also known as linear. It will have a bond angle of 180 degrees. 180 degrees going that way. Why are they the same name? The type of electrons that we have here are bonding electrons. So when those bonding electrons move, the atoms are attached to them. So as those electrons move, so does the atoms. So the entire molecule ends up in the same geometry as the electrons around the central atom, because as those electrons move, the atoms attach, basically move with them. They go up, they go down, they will all move together. So 2 electron pairs and 2 bonds, electron pair geometry linear. Molecular geometry is linear with a bond angle of 180 degrees. The next example is one where we have a central atom and 3 things attached. So once again here, if we look at our boron in the middle, the number of electron pairs here is how many around that boron? 3. 1, 2, and 3. Something with 3 electron pairs, the way the electron pair geometry is arranged is what is known as trigonal planar. Again, in this case, the number of bonds we have are going to be, we have 3 bonds in this case, 1, 2, and 3, right? They're all bonds. The molecular geometry name will also be trigonal planar. Some people call this triangular. That is because our non-bonding electron, our bonding electrons are moving. But in this case, there is a different situation that these guys are trying to get away from each other, but these 2 guys also need to get away from each other so they can't get too close. So what happens is because of that 3rd bond now, they can't really just spread out across from each other like we had with 2. Because of that 3rd one, they can now get into this shape. They call it triangular because it makes like a triangle. Yeah, equal lateral sort of triangle there. Between those 2, bond angle of 120 degrees, basically. So here again, both the electron pair geometry and molecular geometry name are the same because as those bonding electrons move, the atoms that are attached to them will move exactly the same way. So as those move, the atoms move with them, and we end up with the same sort of triangle type geometry here. Any questions on that one there? Next example is something where we have a central atom and 4 things attached. That's really bad. Let's just fix that there. So we'll look something like this here. So when we look at the central atom here, which in this case is the carbon, it has 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs. Again, I am only concerned with the guy, nobody else. So that's the most important one. Pairs is 4. Something with 4 electron pairs, electron pair geometry name is tetrahedral. Now here we have 4 bonds happening. So we do have 4 bonds. And again, 1 bond, 2 bond, 3 bonds, 4 bonds happening here. The molecular geometry name is also tetrahedral. Same idea, except now that we got 4 bonds, right? So we got basically this situation happening where they want to escape each other, they want to get away from each other, but they can't go too far because these guys are kind of in the way now. So they can kind of keep moving until they find like a happy medium between them all. And this gives us this tetrahedral shape. Has a bond angle of 109.5. It's kind of like a triangle on the face and almost like a pyramidal type thing on the bottom. Kind of a triangle on the face of it in terms of that geometry there. Next sort of geometry is one where we get lone pairs involved. Up until this point, both the electron pair geometry name and the molecular geometry name are the same. And again, they're the same because we only had bonding electrons around the central atom. So as I've been talking about, as those bonding electrons move, the atoms that are attached will move with them, and they will end up in the same geometry. So whenever you draw a Lewis structure and there's no dots on the central atom, both the electron pair geometry name and the molecular geometry name will be exactly the same because of that, because as electrons move, so do the atoms. It is only when we introduce non-bonding electron dots on the central atom that the names are different. And the one name that's actually different is molecular geometry name. So the molecular geometry name will change when we get dots around the central atom. The electron pair geometry will still be the same. It's based on how many electron pairs you have. The reason for that is when we get non-bonding electrons involved, we now have electrons that do not have atoms attached to it. So as they move, there's no atoms moving with them. They got a little bit more space. And because of that, they have a little bit more space. It gives those other bonded atoms, for example, a little extra room to move. And then what it does is it changes the overall shape of the molecule. There is 3 types of electron sort of interaction. The best type of electron-electron interaction is bonding near bonding, lines near lines. That's like really tolerable. It's okay. The next worst situation is where you have non-bonding electrons near bonding. They do not want to be near each other. So again, they're going to try to get away from each other as far as possible. The non-bonding electrons don't have an atom attached to it, so they're able to kind of move around a little bit more. So it's going to give them a little bit more distance. The worst possible scenario in terms of electrons being near each other is non-bonding electrons near non-bonding electrons. You have dots near dots, they absolutely positively do not want to be anywhere near each other. So they will try to get as far away from each other as possible. Remember, as these electrons try to move away from each other, everything else that's attached and bonded, well, also has to move, right, in accordance with it. And that's what kind of messes up the molecular geometry name. So as those non-bonding electrons start to move away, bonding electrons will also move away, and it will change the geometry or shape of the molecule because of that. So let's take a look at some examples of this. We're going to look at SO2, and if we draw SO2, SO2 will look like this. I think maybe we drew it earlier, I think. And if we look at SO2, once again, we want to look at the center atom here. The number of electron pairs, how many are there? Doesn't matter if they're dots or lines, how many electron pairs? There is actually 1, 2, and 3. Remember, double bonds, triple bonds, everybody counts as 1. So when we're doing geometry, so especially when you're doing geometry. So there's actually 3 electron pairs. And the electron pair geometry name doesn't change. Something with 3 electron pairs is still trigonal planar. But in this case, what we have in terms of bonds are, how many bonds? We actually have 2 bonds. So 1 bond here, once again, double bond, triple bond counts as 1 bond. So everything when you're doing geometry counts as 1, both the bonds and the electron pairs all count as 1. So we have 2 bonds. So what happens in this case is we have the sulfur here with its non-bonding electrons, which like the oxygens, like these bonding electrons are like, I'm going to try to get away as far as possible from you. And this bonding electron is going to try to get away as far as possible. But at some point, these 2 guys can't get too close to each other either because there's electrons there. So what ends up happening because of that is the molecular geometry ends up being what I personally like to call angular. A lot of people call it angular. Some people will call it bent angular, but we'll go with angular in this class. So 3 electron pairs, 2 bonds is angular. It has a bond angle of less than 120. The bond angle is based on the electron pair geometry name. So because of the non-bonding electron, it's able to sort of contort a little bit more. So we get a little less of a bond angle than 120 degrees because it's missing that third bond. The next geometry is one where we have a central atom here. And when we look at this central atom, how many electron pairs in the central atom there? There are 1, 2, 3, and 4. So when we're doing geometry, it doesn't matter if they're dots or lines, we're counting everybody. And again, everybody pretty much counts as 1. So double bonds, triple bonds, everybody's counting as 1. We're doing electron pairs. So this guy would have 4. Just like we saw earlier, something with 4 electron pairs, the electron pair geometry is going to be tetrahedral. Number of bonds in this case is how many? It is 3. 1, 2, and 3 bonds only, right? So just the lines, right? And again, when you're doing bonds, double bond, triple bond, all counts as 1, would be 3. So same idea here. We have these non-bonding electrons. So what's going to happen is these guys are going to try to get away from those non-bonding electrons. But we have these third bond there where they can't get too close to one another as well. So the molecular geometry name is going to be trigonal pyramid, or pyramidal, sometimes people call it. And the bond angle here will be less than 109.5, which is the tetrahedral bond angle. It's about 107 for this particular one here, is actually the bond angle. Again, is trigonal pyramid because it kind of makes a pyramidal shape on the bottom and a triangle up there up on top is basically the geometry here. For a moment here, let's talk about 2 geometries, trigonal pyramid. And the one we saw earlier, which was trigonal planar, which is 3 electron pairs and 3 bonds, right? They are different. They are different geometries. So if you are going to write your answer, do not just write trigonal and let me choose. I will choose with an X, yes? So choose the trigonal pyramid or trigonal planar. They are different. Don't do my other favorite, which is trigonal. I'm very confident. Clearly is planar pyramid, something like that. I'm not really sure. I should see if it's written there. So they are different geometries. They do refer to different things. So you do have to specify trigonal planar or trigonal pyramid. Can't just write trigonal for those guys. Question on that there. Last geometry that you're responsible for is this one here, like we see in water. Again, if we look at the central atom here, which is the oxygen, number of electron pairs is 4. 1, 2, 3, and 4 electron pairs. Once again, something with 4 electron pairs, the electron pair geometry is tetrahedral. We have, in terms of bonds, only 2 in this case, 1 and 2, right? And what happens in this case is we have all of the bad electron-electron interaction happening. We have non-bonding electrons near non-bonding electrons, which these two, as we talked about, are going to try to go as far away from each other as possible. We also have non-bonding electrons near bonding electrons, which those guys are also going to try to get away from each other. And we have bonding electrons near bonding electrons, which again, they can't get too close. So as those non-bonding electrons go to the sides and out, it's going to cause those bonding electrons to come down. And what happens is that we get a molecular geometry known as bent or V-shaped, which is why water all the time is drawn like this, right? So like a V upside down. The bond angle here is less than 109.5. For something like water, it's like 104, actually, something in that ballpark. Best way to do it is for most people, because a lot of people can't visualize three-dimensional space in their head, myself included, is to look at a chart where you have the number of electron pairs, the number of bonds, and the geometry. So that's really the best way to sort of know it. Here's a table like that from your book. For us, we only lecture molecular geometry names. So we will only be responsible for the shape name. You will not have to do the electron pair name, but you will just be responsible for shape. So really, number of electrons, number of bonds, and shape name basically is what you need to know. And you have a similar table in your book. Any questions on that there? Okay. All right, I think the lab manual does electron pair geometry, if I'm not mistaken. So lastly, here in this chapter, we're going to talk about polarity of molecules. So earlier in this chapter, we talked about bond polarity, where we did the difference in electronegativity values. What we're talking about here is the actual polarity of the entire molecule as a whole. So as a whole, is the molecule sharing electrons equally or unequally? So let's just start with the easiest thing to figure out, which is diatomic molecules. So if I had something like H2, that bond there, is that a polar or non-polar bond? Should those electrons be shared equally or unequally? They are going to share them equally, right? They're both hydrogen, right? Which means if I did the difference in electronegativity value, you would get a difference of 0. 2.1 minus 2.1 will give you 0. This is a non-polar bond, right? Because of the difference in electronegativity. This particular molecule only has one bond total, which means if that one bond makes up the entire thing and that one bond is non-polar, this molecule would also be a non-polar molecule. That is the only place where bond polarity, where you do the difference in electronegativity values, and molecular polarity will be the same, because there's just one bond. And if that bond is non-polar, the molecule will be non-polar. Just like if we had HF, like we saw earlier, that bond between H and F has a difference in electronegativity of 1.9, which is a polar bond, as we talked about. Once again, it only has one bond in this entire molecule, which means that this would be a polar molecule. And because it's a polar molecule, it will have what is known as a dipole moment, which oddly is shown by the same arrow that we talked about when we did a polar bond. It's the same arrow that's used for it. That means that this part of the molecule is more negative. This part is more positive in this case. So if you have a polar molecule, it will have a dipole moment, which will be drawn with that arrow. And that would indicate that overall in the entire molecule, it is unequal sharing of electrons, and there will be a part of the molecule that is more positive and a part that is more negative. If you have a nonpolar molecule, it will be basically a neutral molecule. There will not be a side of that molecule that's positive or negative. It's basically no charge type of molecule. So diatomic molecules, doesn't matter if it's single bonded, double bonded, triple bonded. If the bond in a diatomic molecule is polar, the molecule will be polar, and if it's nonpolar, it will be nonpolar. Now, if everything was that easy, that would be great, but of course it's chemistry, so it's not. So when you have 3 or more atoms involved, you need to look at 2 things. You need to look, are there polar bonds? And you need to look at the molecular geometry or the shape. So let's take a pretty common example, which is one I think we drew earlier, carbon dioxide. So if we draw carbon dioxide such as this, it will look something like that. Is the bond between carbon and oxygen polar or nonpolar? Well, they are in the same period on the periodic table, something like that, right? So in terms of electronegativity, which one should be more electronegative? Oxygen. So is it a polar or nonpolar bond? So there is a difference in electronegativity, and they're in the same row. It is going to be a polar bond, yeah? Because the guy to the right is more electronegative than the guy to the left. That will create a polar bond. So if you remember, we talked about that you could just use the same row if they're in the same row, and that will create a polar bond if they're in there. It is more electronegative. So if we drew the bond dipoles, it would go this way. So it does have polar bonds. But it has 3 or more atoms, so we have to look at the geometry. What is the geometry of this guy? The molecular geometry. If I asked you, what is the molecular geometry of this guy? It is linear because it has, if we look here, 1 electron pair, 2 electron pairs. And it has 1, 2 bonds. So the geometry here is linear. And because the geometry here is linear, it's actually going to be a nonpolar molecule, even though it does have polar bonds. And that is because if it is linear, such as like pen here, and I have oxygen pulling this way, and I have oxygen pulling the other way, am I actually pulling on my pen? Is it going anywhere? It is not. They are canceling each other out, kind of like tug of war. They're both pulling equally and opposite of each other. They actually will cancel each other out. So even though CO2 polar bonds, because of its geometry, it will actually be a nonpolar molecule because they will cancel each other out. Now, if you take something like water, the bond between oxygen and hydrogen is polar, heading towards the oxygen. The geometry of water, as we just saw, is bent or V-shaped, right? So it does have polar bonds. And it is bent or V-shaped in this case. So the geometry in this case, though, is like we have this kind of thing happening, and we got everybody going this way and this way, almost like there's a string up on top, and everybody's pulling from the string from the top. If I pull just from the top of something like that, right, the whole thing you can kind of visualize is going to move, and we will have a net dipole moment happening here, where the oxygen is more negative, hydrogen of water is more positive, and this would be a polar molecule. That is because those bond dipoles are vectors, dare I say physics. They had direction, they have magnitude, and I fell asleep at that point in physics. But I woke up long enough to know that in certain cases, those vectors will add to each other, and in certain cases, they will actually cancel each other out. Cases where they cancel each other out is when they head in equal and opposite directions of each other and are right at each other, they will cancel each other out. Cases like here, they actually add to one another. In case you're curious how that kind of works, it goes like that. You put it head to toe, and then the net dipole is when they add to each other in that direction. Nobody wants to do that. That's like that's like physics. And like I said, I fell asleep, and that's all I remember from physics. So there must be obviously a much easier way to sort of figure it out, and there is. There are certain geometries which are considered symmetrical geometries, and we're talking about molecular geometries here, those names. You guys, you have trigonal planar, and you have tetrahedral. These are symmetrical geometries. What they all have in common is there are no dots on the central atom, no lone pairs. And if you then everything on the outside is the same atom. It will be a nonpolar molecule because they will cancel each other out symmetrically. So if you had something like this, there are polar bonds heading towards the fluorine. It is more electronegative. But when I look at it, I see no dots. And I see everything on the outside is the same. It's going to be nonpolar, this molecule, because they're all going to pull equal and opposite like a rope. Everybody pulling equal and opposite of each other. Nobody's going anywhere, basically. Now, if I switched out one of those fluorines for, say, a hydrogen, what did I just do in this case? I now have 3 polar bonds. This carbon-hydrogen bond is actually nonpolar. You got these 3 guys kind of pulling in this direction. This guy not doing much. He's actually going in the same direction. And it's going to basically pull everybody that way. And it will now become a polar molecule. So if you have trigonal planar geometry or tetrahedral and everything on the outside is the same element, going to be nonpolar. If you have either of those geometries and everybody on the outside is not the same element, you will most likely have a polar molecule. That leaves some unsymmetrical geometries, which in your case is trigonal pyramid, angular. What all these guys have in common are there are dots on the central atom. And if you have any of those geometries and all the outside atoms are the same, it will most likely be a polar molecule because they're not going to pull equally, basically. Like in our case of water, I see dots. I see everybody on the outside the same, polar molecule. That leaves only linear left to decide, and linear is pretty straightforward. You have a linear like in CO2 where they're pointing in opposite directions, it's going to be nonpolar. You have a linear where they are heading in the same direction at each other, going to also be nonpolar. It's like a swinging door, 2 people on opposite sides of a door pushing equally. Door's never going to open, right? So they cancel each other out. But you could have a situation where linearly everybody's heading in the same direction, which means then it would be polar. So linear, since it's a straight line, is pretty easy one to figure out because either they're going to head at each other nonpolar, head opposite of each other nonpolar, or head in the same direction, which would be polar. Any questions on kind of the quick way to do geometry? So just to show you how quick it could be, you could take some of the stuff that we drew and let me just draw a few of these here. Obviously, we did that guy here. We did this guy. I don't know if we did this guy, but I'll put him in. We did. All right, we got that. Looks good. All right, and we got this. All right, here we go. Polar and nonpolar molecule. Central atom, dots or no dots? Everything on the outside is the same or different? Same element. No dots, everything on the outside the same? Nonpolar molecule. Yeah. The one we just did here is linear, right? So obviously this one we do need to think about, right? Going in opposite directions, and they're going to cancel each other out, which would be nonpolar. This one, dots on the central atom? Yes. Everything on the outside is the same. That's going to be polar. Yes. How about this one? Dots on the central atom. Everything on the outside is the same. Polar or nonpolar? Dots on the central atom. Everything on the outside is the same. Polar or nonpolar? What about this one? It's nonpolar as that is a diatomic molecule, right? That one bond is nonpolar, which means this molecule is nonpolar, right? How about that one? And that one. This one is polar or nonpolar. Nonpolar, everything on the outside is the same, and the central atom has no dots. By the way, they're all nonpolar bonds. How about this one? This one's going to actually be polar because everything on the outside is not the same and there's no dots. So that's how you could do polarity, molecular polarity in like 2 seconds. Dots or no dots, basically. Yeah. Everything the same on the outside or not the same. And again, the only one you really have to think about is linear as to which way it's heading. And again, in our diatomic molecules, if the bond is polar or non-polar, we'll tell you what the molecular polarity is. Any questions on any of that there? All right.